So this is a 2-trit counter that I built in Minecraft. Both of these trit displays. These are trits, of course, not bits because they have 3 states. These are balanced ternary, which means that each trit can either be a 0, a 1, or a -1, which is displayed as an L on the system because it looks like an upside down 1. And to demonstrate how a single trit, trit works, I'm going to disconnect this one temporarily. So for now, we're focusing on this trit. This button increments the counter, or this trit display-wise. So this is a 0. Press this button, it adds 1, so now it displays a 1. And now because this is balanced ternary, when you add 1 to a single trit 1, it then goes to -1, or L. So now it's an L for -1, and we add 1 more, it goes back to 0. So that's how a single trit works. Now to bring in back this trit here. Okay, so now both trits are involved. Okay, what is going on here? Okay, I need to reset this. Okay, there we go. So, with 2 trits involved, there's now the 1's place trit and a 3's place trit. And we can start incrementing again. Add a 1. So now this is in the one place trit is in the 1 state. And we add and then when I add another 1 to this, the 1's place trit will go to the L state, and a 1 will be carried over to the 3's place. So this is 1, add 1 more, and so this is 1 is a 3 place, this is a 3, plus an L in a 1's place of -1, so this is 2. This is a 2 in balanced ternary. And then we add 1 more. The 1 minus 1 becomes 0. There. So now we have a 1 in the 3's place and the 0 in the 1's place, so that's 3. And also, because this is just 2 trits, the carry from the 3's trit, which theoretically would go to a 9's trit if there was more of these modules going off in this direction, that signal goes nowhere. And so the next step after 3 plus 1 equals 4, we add 1 here. This trit will go to L. 1 will be carried, which makes this trit go to L. And the next step is -3 minus 1 or -4. This is -4. And as I keep incrementing, it counts up back to 0. This is -1. 0. And now I'm just gonna walk through all the states again. So this is 0, 1, 2, 3, 4, -4, -3, -2, -1, back to 0. Now I can step off this podium and look at how this works. So each TRIT is basically a copper bulb with a redstone torch in front of its output. Two of those linked together around like this, with these two blocks here toggle as an input. And what that essentially does is that this bit here lights up when the TRIT is set to -1, and this light here lights up when this TRIT is in the 0 state, as it is now. It just so happens that toggling this signal makes this this two copper bulb redstone torch setup thingy have 3 states. So that's basically how the one TRIT is set up functionally, and then these two signals are fussed around a bit to get this display to display a 0, 1, or L for -1. And then, as for the carry mechanism, there's a pulse shortener and another copper bulb, and another pulse shortener. All of that just like makes that so when the TRIT goes from 1 to L, it sends a pulse here to this TRIT here, and makes it switch from 0 to 1 to L, etc. And of course, the same logic shenanigans makes the display for the makes the display for the 3's place TRIT, and that's basically how this whole thing works. So yeah, that is my 2 TRIT redstone counter thingy. So yeah, that's basically it. I don't know. Theoretically, I could expand on this into like this this balanced ternary redstone computer something. I know it's theoretically possible, but I know like nobody I've heard of has like dealt with using redstone for balanced ternary as far as I know. So I don't know, it's a possibility, but of course, as you saw from how this counter mechanically works from a moment ago, the mechanisms involved are clunkier than with implementing binary, but like, I don't know, like this redstone ternary stuff would be like a more of a theoretical showcase. Show like that ternary redstone computing is like theoretically possible, even though it's like not as practical. Anyway, that's enough for this video. Bye.